Okay, let's take a look at the type of problem which we're going to be seeing in this chapter. So this is one about an electromagnetic flow meter that is used to detect blood flow in a coronary artery. So let's read it through. Typical blood velocities in coronary arteries range from 10 to 30 centimeters per second. Electromagnetic flow meter applies a magnetic field of 0.25 teslas to a coronary artery with a blood velocity of 15 centimeters per second. This force exerts a force on ions in the blood, which will separate. The ions will separate until they make an electric field that exactly balances the magnetic force. This electric field produces a voltage that can be measured. Okay, so we've got 4 questions here. What force is felt by a singly ionized positive sodium ion? Charges will separate until they produce an electric field that cancels this magnetic force. What will be the resulting electric field? And what voltage will this produce across an artery with a diameter of 3 millimeters? Okay, so let's take a look. At the solution. First piece is our strategize, and I'm going to treat this as a magnetic force on charges problem. And now for my preparation step, what I'm going to do is I'm going to draw a picture. And for the picture, let's take a look at my artery here. Let's suppose it's coming from this direction. Blood is flowing this way, so that's my V. We're putting on a magnetic field. Now I'm going to imagine it's in this direction. Okay, and then it's going to push the charges. Now if I use the right-hand rule, okay, that's going to take positive charges and it's going to push them upward. So positives go that way. Negatives are going to get pushed downward. And so it's going to separate charges across the blood vessel. So at the top and the bottom, I'm going to have different charges. The negative charges will pile up down here. The positive charges will pile up there. Velocity is coming out like so. Magnetic field is going to the right like so. So that's basically the view of the situation. And the first thing we were asked to figure out was what is the magnitude of the force on a singly positively charged sodium ion? Well, the velocity is perpendicular to the magnetic field, so the force is just Q times V times B. And we know the charge, that's 1.6 times 10 to the negative 19th coulombs. And I know the speed, that's 0.15 meters per second, which is 15 centimeters per second. And I know the magnetic field, that's 0.25 teslas. And so I can compute the force, and the force that I get is 6.0 times 10 to the negative 21st newtons. Okay. And I've realized I've kind of jumped ahead to the solve steps. We're doing some solving, but we'll go back and do some preparation for other pieces. Because I want to do some more preparation for the next piece, which was to say what magnitude electric field would exactly balance that magnetic force. Well, let's take a look at the situation that we have here. Okay, so I've got positive charges being pushed upward by the magnetic field. So I need to have those charges being pushed downward by the electric field. And I want the magnitude of those two forces, the force of the magnetic field, to be equal to the force of the electric field, to be exactly balanced. And I know the magnetic force, okay, that's 6.0 times 10 to the negative 21st newtons. And the electric force is just Q times E. But of course, I know what Q is. Q is 1.6 times 10 to the negative 19th coulombs. So with that in hand, I'm ready for my second bout of solving, which is to figure out the electric field that's necessary. And if I do that, the electric field that's necessary to balance is 0.00375 newtons per coulomb. Okay? Then the final question asks, what potential difference would that make across the cell? I'm sorry, across the blood vessel. Because the positive charges got pushed up, negative charges got pushed down. There's going to be an electric field which is directed from positive to negative. So the electric field is directed downward. And as a consequence, there's a downward electric force on those particles. what difference in potential would I get between the two sides of the blood vessel? So if I went and hooked up a voltmeter like so, what would I measure? And of course, we know that the difference in potential is just equal to the electric field times the distance. So what I'd get is 11 microvolts. Now that's a really, really small voltage. Okay, but the particles aren't moving very quickly, and so I expect the magnetic force to be small. So as a consequence, the electric field I expect to be small. And so as a consequence, a small electric field across a small blood vessel I expect to produce a fairly small potential difference. And so the small potential difference, the small electric field, and the small value of the force all seem quite reasonable. And so my last phase is looking at the assessment, and this all makes sense.